Hello everybody, this is Rudra Pradhan here. Welcome to Engineering Econometrics. We will continue with time series modeling again, and that too the same volatility modeling. We stopped earlier that to the requirements of arch and gauge estimation. We have already highlighted the arch structures and the gauge structures and the kind of difference, the kind of need, and the kind of flow, how to start the process, and then we like to know what is the kind of estimation mechanism, because compared to autoregressive model, then moving average models and ARIMA model, these two clusters are nonlinear in structure. That is why it is slightly different from the estimation process compared to ARIMA model. So, it is technically step by step process like we do in ARIMA cluster. In specific, we start with first mean equation, that is here with respect to one variable, and that too let us say AR1. AR1 stands for autoregressive 1, and which is the first hand entry to the arch and gauge modeling, and for that we like to estimate these equations. Y t is the original variables and y t minus 1 is the lag variables, and as usual we can run the model like simple regression modeling, that too through OLS mechanism, and error must behave like this. And after getting the estimated y t, we can have the error term u t and square of the error terms and error variance, and then we can connect like this: sigma square t equal to alpha 0 plus u square t minus 1 and the coefficient alpha 1, again beta coefficient with respect to sigma square t minus 1. Now, this is step 1, and in the step 2 this is what the model we need to estimate, and in the first hand this is the mean model, and that too can be followed with OLS, and this is nonlinear model. So, we cannot actually directly go through OLS, rather we use a technique called as maximum likelihood estimations. That is what technical called as a MLE, maximum likelihood estimation technique. And the general framework of maximum likelihood estimation is like this: starts with L equal to minus t by 2 log 2 pi, that is actually it follows with the normal density function, and minus 1 by 2 sum of log sigma square and minus 1 by 2 y minus mu minus psi u t minus square by sigma square. That is what the kind of starting, and the software will actually maximize this function and give the parameters values and their standard errors. So, that means technically we look here the values of parameters, that to alpha 0, alpha 1 and beta. That is the kind of things we are supposed to have here. So, accordingly moving forward we will have the equation like this. This is another kind of structure where we are connecting the bivariate regression y t as a function of x t. If you compare with the previous ones, it is y t as a function of y t minus 1, and here y t depends upon another independent variable and as usual you can go for this is the mean estimations, and that too have through OLS mechanism. Assuming that error term is normally distributed with 0 mean and unit standard deviation. As a result, the probability density function for a normal distributed random variable with this mean and variance is given by this particular structures. Okay. So, that means technically this is what the exact which we have already highlighted the previous slide, that is with reference to the mean equation, this ones, that is what y t minus. So, this is what the mean equation, and here the same things, this is what the mean equation. Now, successive values of y t would trace out the familiar bell shaped curve, that is the NDF. Assuming that error term UTR identically independently distributed with 0 mean and unit variance, and then y2 will also similar structure followed by normally distributed with mean 0 and unit variance, and then we have a joint probability density function for all the y's, and that can be expressed as a product of the individual density functions. So, ultimately you will have the structure like this, and then after simplification the particular setup will transfer into the maximum likelihood estimation process. That is what the maximum likelihood estimation. So, now again taking the clue from this equation, we can proceed further, and the whole transformation will be likelihood functions, that is with respect to beta 1, beta 2 and the standard deviation sigma square, and maximum likelihood estimate involves choosing parameter values that maximize these functions. That means, technically as usual like OLS, MLE procedure is also similar, where we can actually optimize with respect to beta 1, beta 2 and sigma square. So, that means technically, so we like to differentiate with respect to DLF with d beta 1, with respect to d beta 2 and with respect to d sigma squares, like as usual OLS mechanism. And by setting these three equations to 0 and simplify, we will have the values of the parameters beta 1, beta 2 and beta 3. So, that means technically if you move further as per the given instructions, so we will have like this, and the first one that to differentiate is with respect to d LLF by d beta 1s is this much, which is equal to 0. Again d LLF by d beta 2, which is this much. That means, this value should be equal to 0, and again d LLF by d sigma square, which is equal to this much. So, all will set to 0. So, that means technically we have 3 parameters as usual, actually like trivariate a simple linear modeling, and we have here this is the first one which we can actually which we can have here with respect to beta 1. Okay. So, that means technically this one, which is also equal to 0, and then so technically so this equal to 0, this equal to 0 and this equal to 0, and if you simplify, then we have 3 different equation here. Okay. So, the first one, okay, first one. So, this is what we have received, that is with respect to the first equation, this one, and then this second equation, and after doing all the simplification, finally we will have beta 1, beta 2 and sigma square. So, that means technically you will have beta 2 like this and sigma square like this. So, then again after simplification, if you move further, then sigma square equal to simply u square by t. That is what called as error variance. Compared to the Wallace mechanism, which you have already received sigma square. Okay. So, technically that time we reported sigma square equal to summation e square by n minus 2 for bivariate, n minus 3 for trivariate, and this is a trivariate structure altogether, but maximum likelihood estimation is having only this much, sigma square equal to summation e square by e. So, now the question is how do this for the kind of value have a connection with Wallace estimators. That means technically what I have written here, so it is here all. So, it is actually t minus k, that is what is the degree of freedom. So, therefore, maximum likelihood estimator of the variance of the disturbances is biased, although it is consistent. Now, the question is how does this help us in estimating heteroscedasticity models? That is the big deal which you need to highlight here. Now, coming to the mean equation again, which you start from the beginning, that to y t as a connected to log of y t minus 1, where error term follows mean of the error term and unit variance, and followed by sigma square equal to alpha 0 alpha 1 square u square t minus 1 and beta sigma square t minus 1, and then the likelihood functions. Okay. However, the likelihood functions for a model with time varying variances cannot be maximized analytically except in the simplest of cases. As a result, the numerical procedure is to maximize the log likelihood functions. Technically, the potential problem is to look for local optima or multimodalities in the likelihood surface. That means, technically the optimization procedure will follow to set up the likelihood functions, use regression to get initial values of the parameters, mean parameters, choose some initial structure for the conditional variance parameters, and then finally specify a convergence criteria either by criterion or by a value. Okay. So, that is what the procedure you have to follow. Okay. Now, to extend these ones, we can recall that the conditional normality assumption for u is essential. So, we can test for the normality using u t equal to another error term b t and the standard deviation sigma t, where b t will follow normally distributed mean 0 and unit variance, and the sample counterpart is sigma t equal to alpha 0 square root of alpha 0 plus alpha 1 square t minus 1 and alpha 2 sigma square t minus 1. So, as a result b t equal to simply u t by sigma t, and hence the estimated of v t will be estimated of u t by estimated of sigma. Now, the question is whether the estimated v is normal. In reality, v estimation are still leptotic, although less, so that means compared to u t. So, now question is this a problem? Frankly, it is not really, as we can use the maximum likelihood with a robust variance and I think or can say covariance estimator. So, maximum likelihood with robust standard errors is called quasi maximum likelihood or simply called as QML. Again, taking the clue, we have the Gauss model and where a huge number of extension and variants have been proposed. That is what I have already highlighted. That means, the Gauss clusters we have actually a basket that is starting with simple Gauss, then E Gauss, GJR and Gauss M models. So, problems with Gauss PQ models, first the non-negativity constant may still be violated and Gauss models cannot account for leverage effects, which you can take care through E Gauss or GJR. Possible solution actually, that is what the kind of structure through E Gauss, that is called as exponential Gauss, and the kind of GJR models which are actually simply called as asymmetric Gauss models. So, let us see how is this particular structure, that is with respect to E Gauss, GJR and Gauss M models. And in between we have already highlighted a component called as a I Gauss. So, that means we have actually plenty of baskets, and starting with the first E Gauss, that is actually the extension of Gauss model. So, here the general framework of E Gauss is like this, just extension where error variance is connected with the square of the error variance, and then the additional part which we will have here is like this, that is just extension to this case. Earlier we have y square t minus 1 and g square t minus 1, now it has some kind of an extension with respect to u t and g t and sigma t. So, the advantages of this model are, since we model the log sigma square, even if the parameters are negative, then sigma square will be positive. So, that is why some adjustment need to be taken care. We can account for the leverage effect if the relationship between volatility and the returns is negative, and that will be the negative one. So, for that means this particular component. So, there is a technically another parameter which can actually bring the kind of difference in the case of EGACH, and then the other form is called as GJR model. It is actually developed by three great statisticians according to their name, and the typical structure of this model is like this. It is again extension, this part is actually GACH, and then this is the extra extension which we like to have, and the IT minus is the kind of connecting point. It is like two different breakups. Okay, that is what the kind of leverage effect. One is IT minus 1 equal to 1 if UT minus 1 less than 0. If not, it is equal to 0. That means, when UT minus 1 greater than equal to 0, then IT minus 1 represents 0 value. That means, by default we can have another variable which we can include into this particular GACH model, and for a leverage effect we would see whether the particular parameter will be positive one. The need is that alpha 1 plus the leverage parameter should be greater than equal to 0, and alpha 1 for its non negativity, that means that this component, that is the structure of GJR. Of course, this is actually a technical kind of understanding, but ultimately if you use the software by default will give you the kind of results very easily. Just we have to set the mean equation, and then we go to the variance equation by setting these arch and GACH models. If you ask the software to give the arch estimations, and that too we have to just fix the log length. Of course, manually you can put one after another and test, but software by itself will give you different results if you starting with putting log variance. Similarly, in the case of GACH, and again you can have different GACH outputs by changing the log order 1 1 2 2 and so on, and again we can ask the software to give EGACH results and GJR results and the kind of GACH M types of models. So, all are it's there. So, just you have to follow up it, and then you can have the estimated results. So, that means technically the model is very clear, or here the major kind of structure is that we are predicting a kind of engineering variable, that too through a error component, and the starting is actually the variable can be first linearly connected with the log variable, and then have the error term, and through the error term again the kind of prediction we are doing. So, we like to check how effective is this particular process to predict the y variables, or we have a structure y t which can be influenced by some of the independent variables, not necessarily that log variable, and then again that will be the mean equations, and you can have the error term, and the error term can be used as a instrument again to predict or to to forecast the particular dependent variable. The way I have cited the example of rod penetration or something kind of rod density, that too with respect to different variables like rod investment in other transportation and so on. So, that is what the kind of different structure of the models through which you can generalize. Okay. So, for examples, if you go through estimation process, the mean equation will be like this and the variance equation will be like this. Of course, there are lots of reliability checks or robustness checks to do this, and first hand requirement is actually as usual to check whether the parameters are statistically significant, and then the overall fitness, and as a result the particular error variance can be used as an instrument to predict the kind of engineering variables. Now, this is another kind of see kind of market information which can be used as an instrument in the case of Arch and Gauge model and different kind of Gauge model. This is stock market problem technically, and usually this kind of models more frequently used in financial engineering rather than simple in other engineering like civil engineering or some kind of mechanical engineering, etc. So, that is what the kind of structure, and coming to the kind of structure, because why this we use this ones, because this one will actually create a two different structure altogether. So, that means if you look into the kind of shape, there is one structure declining, the another structure is increasing. So, by default you like to find out the kind of structural change which can affect the ultimate dependent variables. Since the behavior of the variable is changing route from one direction to another direction, so the essential structure of Gauge model can be can be modified accordingly, provided if the variable behavior is like this. Otherwise, you can simply estimate with Arch or Gauge model. Then Gauge Gauge in mean kind of structure, we expect a risk to be compensated, like again in the financial engineering scenario. So, why not let the return of a security be partly determined by its risks. So, technically, so the model is actually Arch M specification, then Gauge specification. That means, technically we start with YT, again mean equation and the kind of variance equations, but here delta can be interpreted as a sort of risk premium. Again, it is impossible to combine all or some of these models together to get more complex, that the hybrid models like ARMA eGauge 11M model, but that is the thing which you can have in the process. Means it is a kind of more complex kind of character through which you can do the processing. Now, so for a use is concerned, what type of Gauge models we need all these things. So, Gauge can model the volatility clustering, that to study the effect. Since the conditional variance is autoregressive, such models can be used to forecast volatility simply. So, the procedure is actually you have to find out the variance vectors, and so modeling will be done through actually error variance, and that itself will be used to forecast the main variable, let us say YT. So, variance forecast are additive over time, that is what the means you can say that it is the big advantage of this particular process. Okay. So, now some of the kind of examples which you can bring here, that usually the main aim of this particular cluster is to consider the out of sample forecasting performance, that of Gauge and eGauge models for predicting the stock index volatility, particularly the case of financial engineering, and implied volatility, that is the market expectations of the average level of volatility of an option. Now, the question of which is better, Gauge or implied volatility. So, actually it is the kind of situation you have to check, and over the time you have to compare, and one examples which you have citing here. It explicitly depends upon data structure, and starting with this data structure, we start with mean equation and then the variance equation here. So, these base models will be like that, the mean equation, and then we can have the variance equations, and then the kind of its extensions. So, now it is actually extension of capital asset pricing model. Okay. So, return on the market portfolio and denotes the risk free rate. So, ST denotes the conditional variance from the gas type models, while sigma square T denotes the implied variance from the option prices. That is the kind of so actually this kind of model is highly useful for financial engineering, the way I have already highlighted. And so, that means technically we must have a time series data and some of the kind of extensor or information which may be highly actually useful for this kind of modeling. Again, adding a log value of the implied volatility parameter to equation, we have the following again, and that is what the kind of another extension. Here we have these are all conditions, null hypothesis to set the delta equal to 0, okay, corresponding to these ones, and then at rest alpha 1 equal to 0 and beta 1 equal to 0, and further we have actually the condition with respect to this model. So, these are all as usual procedure to set the null hypothesis, and then as usual go by the estimation process, we can have the following outcome. And since we have used a particular data set, and then various types of model which we have here, starting with the mean equations, variance equations, and the extensions, EGACH and the kind of implied volatility. So, we have the estimation process, and then you are supposed to check whether the particular parameters are statistically significant, and then the log likelihood ratio, the chi-squares. So, these are all actually will support the particular model ultimately. So, we like to check whether these parameters are statistically significant, or that means we can say that the volatility component will be very useful for predicting a kind of engineering variables. So, that is what the kind of case, and again if you extend these models, we have actually plenty of results. That is the kind of extension to EGACH versus implied volatility. Okay. So, that means technically we have actually variety type of means various types of volatility modeling. That means we have lots of variety so far as Arch and Gauss clusters are concerned, and then on the basis of these models, you can actually predict some of the engineering variables. More specifically, this kind of models are more frequently used in actually financial engineering, what I have already highlighted categorically. So, that means on the top of this discussion, that too in time series modeling. So, this is a series of models which can be frequently used to predict some of the engineering variables, where actually volatility is an issue. You can simply find out the standard deviation and then check whether there is a high kind of instability or something like that. So, that you can use these models and predict the kind of engineering output as per the particular requirement and the kind of need. With this we will stop here. Thank you very much.